Hello, this is Miss Moore, and today during chemistry, we're going to do a small discussion on reaction rates. So today's essential question: what is a reaction rate and how is it calculated? So let's start with a really quick review on chemical reactions. A chemical reaction involves the change in composition or makeup of a substance. So what happens is that with the reactants, the thing you're starting with, bonds are broken and the atoms or ions are rearranged. On the product side now, you make new bonds to create new substances. And when a reaction is occurring, there will be a decrease in the amount of reactant and a corresponding increase in the amount of product. Now, this is super, super important. That as a reaction is occurring, the amount of reactant is going to decrease. And at the same time, you're going to get an increase in the amount of product. Now, I know this sounds obvious. Hopefully it sounds obvious. But I really want you to keep this in mind. It is actually really important. All right, and onward. This process can be extremely fast. So we're talking seconds or even less than seconds, or really, really slow. A chemical reaction can take hours, days, or even years. All right, on to reaction rates. We'll start with some definitions. So first of all, when we talk about rate is a measure of the speed of any change that occurs within an interval of time. And then specifically, a reaction rate is the amount of time it takes for a reaction to occur. And we can view the rate of a reaction in three different ways. So basically, this is how we would measure the rate of a reaction, which is actually what we're going to spend the majority of the unit on. So first is the rate of disappearance of a reactant. How long does it take for a reactant to disappear or to reduce? The rate of appearance of product, or the rate at which the overall reaction occurs. So today we are going to spend time talking about those two. So to calculate the rate of disappearance of a reactant, we are going to use this guy here. Negative triangle square bracket reactant over triangle T. So what do all those things mean? Let's start with the triangles. Those triangles mean change. Delta. Change is this triangle, which is actually called delta. Okay? Square brackets. So these square brackets mean concentration. Okay, and usually concentration, the units for concentration, usually are going to be molarity, capital M, so molar. And remember that molarity equals moles over liters. So you can think of it as how many particles, moles, in a certain volume, liters of solution. And let's see, the last one we have here is the little t, and T stands for time. And the time unit can be pretty much whatever. You just need to make sure you write whatever it is. So it could be in seconds, minutes, hours, days, pretty much whatever. Right, so when we're talking about change in the concentration of the reactant, the way you would calculate change of something would be initial concentration and final concentration. So it's going to be final concentration minus initial concentration will give you the change in concentration. Okay. You will note here that for calculating the rate of disappearance of a reactant, it's got a negative sign. The reason for that is because we're disappearing. the reactant concentration is decreasing, right? Which means that this is going to be a small number minus a bigger number, which is going to give us a negative number. And rate is always given as positive. So the rate is always positive, so we need to put a negative sign there. That's sort of a hard way to remember it. In my opinion, what I think of is that you have to put a negative because it's going down, right? So the concentration is going down, so you have a negative there. Anyway, the rate will end up being positive in the end. And then change of time, same as change in reactant. You're going to take the time final minus the time, minus the time initial, and that will give you change in time. So, looking at the formula, you can see that the units for reaction rate are concentration molarity over some time unit. To calculate the rate of appearance of product, you are going to use a very, very similar formula. Change in the concentration of product over delta T. You will note this time, that there's no negative sign, it's positive. That's because when we look at the change in concentration, so concentration final minus concentration initial, we're looking at it, you're adding more product over time, right? So this should be a bigger number minus a smaller number, giving us a positive number. And all rates need to be positive, like I just said, so positive for all rates, which is why there's no negative sign in there. The way I like to think about it instead of all of this stuff, because I think that's sort of confusing, is that you're adding appearance, you're adding product, so it's positive. Where with the reactant, it's disappearing, right? You're reducing the concentration of reactant, so it's going down, so it's negative. So up to you how you want to think about it. Okay, so really quickly, when we're using either change in the concentration of products over delta T or negative change of the concentration of reactants over delta T, what we're getting is an average, it'd be great if I could spell, an average reaction rate. Okay. So why average? Because at any one instant in time, the reaction may be going faster or slower than the speed over a large unit of time. Okay, so what we're calculating here is average reaction rate. And onward, kinetics. So there is a relationship between the rate of disappearance of reactants and the appearance of products. So the rate at which one species, the reactant or product, disappears or appears can be used to find other rates. So let's think that through for a moment. So let's say we have hydrogen gas and oxygen gas. They react and form our favorite, water. Well, we'll keep it in the gas phase. Okay, now what do you always have to do with an equation like this? You have to balance it, right? So we have 2 oxygens on the reactant side, so that means we need 2 oxygens on the product side, which we now have, but now we have 4 hydrogens on the product side, so we need 4 hydrogens on the reactant side. So there we go. So now if you talk about moles, or number of molecules if you prefer, it takes 2 hydrogens and 1 oxygen molecule to make 2 water molecules. So now, think about this for a minute. What is going to be the rate of disappearance of hydrogen versus oxygen? Won't the hydrogen disappear 2 times faster than oxygen? And won't the water appear 2 times faster than oxygen disappears? That makes sense, sort of weird, but think it through. For every 1 oxygen used, there are 2 hydrogens used. So the hydrogens are going to be used twice as fast as the oxygen, right? And for every 2 waters made, 1 oxygen is used, which means the water is going to appear twice as fast as oxygen disappears. And then if we want to compare the hydrogen and the water, it's a 1-to-1, right? So for every 2 hydrogens, there are 2 waters, or for every 1 hydrogen molecule, there is 1 water produced. So there's definitely a relationship here, right, between the rate of the disappearance of reactants to the rate of the appearance of products. All right, so that's the thought process. Let's make this a little more formal. Let's use our same example. So we had 2 hydrogens plus a molecule of oxygen producing 2 water molecules. Okay, and remember our formulas. We had negative change in concentration of the reactants over change in time, and change in concentration of products over change in time. And this is our rate reaction. So remember that we lose hydrogen twice as fast as oxygen. But we would rather have everything be in 1. So what we can say that the rate equals 1/2 change in concentration of hydrogen, change in time. Yep, forgot a negative there. Let's put that negative in, right? That also equals the change in concentration of oxygen over the change in time, which equals 1/2 change, forgot the delta, change in concentration of water over change in time. So what I did is I took the coefficients and put them over 1. The reason I did that is that'll give you a rate of 1, right? So we're basing it, we're just getting rid of the coefficients. It's one way to think about it. Okay, so this is a way, so let's say I knew the rate of reduction of hydrogen gas, I could then figure out the rate of production of water. Okay, so let's write a general equation. So if I had some equation where the coefficient, we have coefficient A, molecule A, plus coefficient B, molecule B, produces coefficient C, molecule C, plus coefficient D, molecule D. Okay, so those are our molecules. And the lowercase letters are our coefficients. Okay, so a general formula for figuring out rate would be rate equals 1 over coefficient A, change concentration of A, change in time. That's a negative because it's a reactant. That equals 1 over the coefficient B, change in the concentration of molecule B over change in time, equals positive 1 over the coefficient C, change in the concentration of C over change in time equals, wish I had a little bit more room, 1 over coefficient D, change in concentration of D over change in time. Okay, so if you know this formula, this is kind of a formula, if you know, then if you're given or solve, let's say for the reaction rate of B, you could calculate the reaction rate change in concentration over time of anything else. All right, let's try this real quickly. Let's say we had nitrogen gas plus hydrogen gas producing ammonia. And we know that the rate of disappearance of hydrogen gas is 0.074 molar per second. So what we want to know is what is the rate of nitrogen gas being used. All right, so the first thing we need to do is figure out the rate expression for this reaction. So the rate equals negative change in concentration of N2 over change in time equals negative 1/3 change in concentration of hydrogen gas over change in time equals 1/2 change concentration of NH3 over change in time. All right, so we're interested, we know the rate of H2, and we're interested in the rate of N2. So we're going to say, let's see, H2, so we have negative 1/3 change in concentration H2 over change in time equals change in concentration of N2 over change in time. So let's plug those numbers in. We have negative 1/3, and then we know this is this, so 0.074 equals change in concentration of N2 over change in time. So basically to get the rate of N2 disappearance, we solve for this guy here, and that gives us, I'll write it up here, that gives us 0.026. There you go. Fairly easy. Okay, let's try one more. Let me get rid of all this mess here. Just keep the stuff we're using. All right. So now what we want to know is what is the rate of the appearance of H2O. Okay. So basically the same thing. We know that we have negative 1/3 change. Let's try that again. Negative 1/3 change in concentration H2 over change in time equals 1/2 change in concentration of water over change in time. Right. So just again, let's just plug this stuff in. Change colors, make it a little easier. So we're going to have negative 1/3. We're going to use this guy right here. 0.074 m over s equals 1/2 change in concentration over change in time. And remember, this right here, that whole thing is the rate, okay? So that's our x, that's what we're solving for. So I guess we could rearrange a little bit. We want to get the part I boxed in yellow by itself. So change color again. To get rid of the 1/2, we'll multiply both sides by 2, giving us 2/3. Okay, so now, again, we want to figure this guy out. So we just need to solve for this, and that gives us 0.049 m per s. Okay, math hopefully isn't too hard. It's really important, though, that you understand the reason why. And I guess that's it for today. Have a good one.